So we just talked about how do we take these atoms and combine them together to make ionic compounds. And remember, an ionic compound was always a metal, something from the left-hand side of the periodic table, plus a non-metal, something from the right-hand side of the periodic table. And when we make those ionic compounds, we combine them in different ways, but our goal was always to balance out the charges. So when we had Na, sodium, which likes to make a plus, Cl minus, which likes to make a minus, we combine them to get NaCl. On the other hand, when we had potassium, which likes to make a plus, and O, which likes to make 2 minus, again, how do I figure those out? I look at my valence electrons, right? 6 valence electrons in oxygen. Easiest way to look like a noble gas is to get to 8. That's taking 2 electrons, and so you get a 2 minus. And in order to balance those out, I'm going to need 2 of those pluses, right? So I'm going to end up with K2O. How do we name these things? Well, it turns out you actually already know how to name them, probably, because you know how to name this guy. What's the name of that one? NaCl, table salt, is called sodium chloride. Right, we took the name of the metal and we combined chloride. What was that IDE ending? That IDE ending told me we had an anion. So we took the name of the metal and the name of the anion and combined them together to make the name of our compound. So we can do the same thing down here for our K2O. You're like, well, no, Professor Clements, this guy's got 2. Don't I need to tell somebody that there's 2 of them there? And it turns out the answer is no. Why not? Because when you said, hey, I've got potassium and oxygen, did I have to tell you that there were 2 in order for us to come up with K2O? No. We came up with K2O by balancing the charges. And there's only one way to do that. So in my name, I don't need to tell you that there's 2 potassiums because you can figure it out. So we're going to use the same thing. We're going to use the name of the metal, potassium, and we're going to use the name of the anion. This is oxygen, but if you remember, we end with the ide, usually the first symbol, ox from oxygen, and we end with the ide, and we have potassium oxide. Let's do some more. Let's go ahead and try some, I don't know, sodium. No, we just did sodium. Let's do lithium. Lithium we know has a +1 because it's an alkaline metal, and we're going to go ahead and combine that with nitrogen, which we know has a 3 minus, right? Nitrogen has 5 valence electrons, 5, 6, 7, 8. That's how we get to our nearest noble gas, is by taking 3 electrons. I can't balance out a +1 and a -3. I need 3 +1s. And so what do I end up with? I end up with Li3N, 3 lithiums and 1 nitrogen. And what am I going to name it? I'm going to name it lithium nitride. I don't say di, I don't say tri. We'll hear those, and you'll hear those in names of molecules. People say carbon dioxide. But that's a different kind of thing. When we have a metal and a non-metal and ionic compound, we're never going to use the dis and the tris and things like that. We just say lithium nitride, and from that, someone should be able to write that formula. So let's go do it that way. Let's say, how do we go from a name to a formula? How do we go from a name to a formula? So if I say, oh, you know, I've got some barium iodide on my shelf, how can I find the formula for barium iodide? Well, remember, in the naming scheme, that first one is our cation. It's our metal. So I find barium on the periodic table. It's Ba. I notice he's in the alkaline earth metals. All the alkaline earth metals are +2 because they all have 2 valence electrons. Easiest thing to do is get rid of those 2. Then I find iodine on the periodic table. You're like, well, shouldn't I look for iodide? Now remember, IDE says I've got an anion, and it starts with iode in this case. And so it turns out it's iodine. I find that on the periodic table. It's I. I notice iodine is one of the halogens. So what does fluorine do? Fluorine has 7 valence electrons, 1 more to get 8. So that's what iodine does as well. So now I've got Ba2 plus and I minus. What do I need to balance that out? I need a second I minus, and I get BaI2. Again, when we write these formulas, we do not write that 2 plus and that minus there. We just write BaI2, barium iodide. So we can do that anytime we've got a name to go to the formula by first writing out the charge of each of them and then balancing them out just like we've done before. So we now know how to go from a formula to a name and from a name to a formula for ionic compounds. But so far, even though I've said metals, we've only stuck with the alkali metals and the alkaline earth metals. And the reason is those guys are easy. Because it turns out every alkali metal is a +1. Every alkaline metal is a +2. But are there cases where we don't know? And the answer is, unfortunately, yes. And those are our transition metals. So here's a table that's just showing some of our transition metals. In fact, lots of our metals. You look here, the alkali metals, you notice those are all +1. The alkaline earth metals, all +2. And all of our non-metals over here, we figured out a lot of those 1 minus, 2 minus, 3 minuses. But if you look here in the middle of the periodic table, they start to list more than one different charge. And they're like Fe2 plus and Fe3 plus. Remember, Fe is iron. So how do we know if it's 2 plus or 3 plus? And the answer is someone's going to tell you. Someone's going to tell you whether you have Fe2 plus or Fe3 plus. They control it by doing chemistry in certain ways. But by the time it gets to you, they already know. And so someone has to tell you, do I have iron with a 2 plus or iron with a 3 plus? Because we can make either of them in the world. So let's do that one as an example. Fe2 plus, and I want to combine that with oxygen. Do you remember oxygen is a 2 minus? How would I combine that? +2 and -2. Well, I'm just going to combine that one of one and one of the other, and I get FeO. Now, if I get FeO, what does my naming scheme from the previous slide tell me? I should call this iron oxide. Right? I just say the name of the cation, the metal, and the name of the anion. Great! But what if somebody did some chemistry and instead of Fe2 plus, they did some chemistry with Fe3 plus, and they combined it with O2 minus? Well, now those don't balance out 1 to 1. I'm giving away 3, I'll take 2. That doesn't balance out. What do we have to do? We have to make sure they balance out. For 3s and 2s, I often use what's called the switch rule. Okay? Don't use it all the time. 3s and 2s, it's great to work with. Other times it can confuse you and get you the wrong answer. But what does the switch rule mean? It means that if iron has a 3 and oxygen has a 2, when I make the formula, what I'm going to get is that iron has the 2 and oxygen has the 3. And my formula looks like Fe2O3. And if I use the same naming scheme I had before, iron oxide, because I told you all, I don't need to tell you how many you have. You're like, but in this case, I get FeO and I call it iron oxide. I get Fe2O3 and I call it iron oxide. That doesn't work. I've got 2 chemical compounds that I'm calling the same thing. And so we need a way of distinguishing between FeO and Fe2O3. And you ready for this? What people decided is they were going to use Roman numerals. You thought you left those way, 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 way back in your life. But we use them in chemistry. And what do we do with the Roman numerals? Well, it turns out with the Roman numerals, we take the charge of our cation here, +2 on the top, +3 on the bottom, and put it in parentheses right here. And remember, Roman numeral 2 is just II. Roman numeral 3, III. And we write our name like that, with the parentheses containing Roman numerals of the charge of our cation. Whew, you might have to review that and replay that a few times. Roman numerals indicating the charge of our cation. So the first one up here, FeO, I wouldn't call it iron oxide. I call it iron 2 oxide. We just say the 2 out loud. We don't say the Roman numerals. And the one on the bottom, Fe2O3, I call iron 3 oxide. Now be very, very, very careful. People want that 3 there to tell me that I've got 3 oxygens, that I've got 3 irons, sorry. Do I have 3 ions? No, I don't. I only have 2. Right? Over here, I've got a 2. Do I have 2 ions? No, I don't have 2 of anything. That 2 is just telling me the charge, and I still need to do that work of balancing out the charges like we've been doing in the last several slides. Let's do another example. Let's take some cobalt, and I'm going to take cobalt 2 plus, and I want to combine that with some bromine. So we find bromine on the periodic table. It's a halogen. All the halogens form a minus. So how am I going to combine those two? I've got a +2 and a -1. I need 2 of those bromines. And I get a formula of COBr2. And what do I name that? Well, the first thing I need to do now is I need to look up where is my metal on the periodic table. I swap over to my periodic table. I notice cobalt's in the middle there, number 27. He's in the transition metals. Anytime you have a transition metal, you need to make sure to put those Roman numerals. Okay, so I now have my COBr, and I'm going to call it cobalt. I'm going to put those Roman numerals in parentheses. The name of my anion is the bromide. And what do I put in parentheses? Do I put a 1 because I've got 1 cobalt? No, I put a 2 because of the charge of the cobalt. Cobalt 2 bromide is the name of COBr2. And we can do the opposite way. We can go from a name to a formula. So let's take titanium 4, and let's go ahead and pair that with sulfide. Okay, titanium 4 sulfide. What am I going to do going from a name to a formula? Well, just like I did last time, I'm going to take that titanium, turn it into a chemical symbol. And what charge do I give it? With the alkali metals and the alkaline earth metals, we had to know which it is. Here, somebody gave me that information. And so I've just got a 4 plus there. Remember, IV in Roman numerals is 4. Sulfide, I just go to the periodic table. I get my S, and that's 2 minus because it's got 6 valence electrons. Would like to have 8. How am I going to find +4 and -2? I just need 2 of the -2s. Right, so now I've got a +4 and a -4, and I get TiS2. And that's my formula for titanium 4 sulfide. So lots going on here about naming transition metals. But we're not done yet. So far, we've only dealt with elements on the periodic table: titanium, oxygen, phosphorus. But it turns out there's a lot more on the periodic table, not just names of individual elements. And so we're going to have to kick this up even one more notch as we go forward. So take a moment. What would be the name of a compound when vanadium with a +3 charge combines with oxygen? Take a moment to try to answer that one. Okay. What did you come up with? Well, with vanadium with a +3 charge, find vanadium on the periodic table. It's in the transition metals. And so we know we're going to be using the Roman numerals. So we can cross off B, we can cross off C, because we know Roman numerals are involved. It's got a +3 charge, so in my Roman numerals is the 3. And now A must be my answer. But it combines with oxygen. Oxygen is going to be the anion. We call it oxide. And my answer is A here, vanadium 3 oxide. Now you'll notice, what didn't I have to do? I didn't have to find the formula of vanadium 3 oxide in order to be able to write its formula. I just needed to know it was vanadium 3 plus and oxygen. All right, the part that nobody likes. What happens when we get slightly more complicated? What happens when we start to add these things that are called common polyatomic ions, or anions? Well, what does polyatomic mean? Poly, many, atomic, atoms. So you've got anions that are made up of many atoms. So far we've had things like S2 minus, we've had Cl minus, just an atom with a charge. Chlorine takes on 1 charge, becomes chloride. But it turns out there's a ton of molecules out there that the whole molecule takes on a charge. So I'm going to zoom in this real quick, and let's take this one, for example. CO3 2 minus, we call it carbonate. You've probably heard of carbonated beverages before. Okay. Carbonate, what is that? Well, it's a carbon attached to 3 oxygens, and that entire molecule takes on a -2 charge. It's not the carbon taking on a -2. It's not one of the oxygens taking on a -2. It's all 4 of them together taking on a -2 charge, taking on 2 electrons from something. Just like we had S2 minus, right? Sulfur took on -2 charge because it needed those to be happy. There's a bunch of molecules out there, some of which we run across a lot. We call them common anions. Like carbonate, the whole molecule takes those 2 electrons. Other ones you've probably seen before. You've probably heard of phosphates. Right? You have probably heard of cyanide. What's cyanide, right? What they use to kill spies, right? Cyanide. You've probably heard of nitrates and nitrites, especially if you like bacon and other highly flavored foods. They've got a lot of nitrates and nitrites in them. You've probably heard of ammonium. So some of these common ions you've heard of before. Now, what are we going to do with those? Well, we're going to use those to name molecules that contain them. But luckily, even though these things look really, really complicated, when you name them, you're just going to use the name of the common ion. Examples are most useful here. Me just talking about it is probably more confusing than anything else. So I've got a few examples here on the left. I've got CaCO3, so calcium and CO3. That's the one we looked up here, which was called carbonate. Now, how did I know the formula was CaCO3? Well, Ca we know, right? It's got a +2 charge. And now we're learning this new thing called carbonate, which has a -2 charge. And again, one of the things I told you at the very beginning, when you start putting the letters, it gets a little confusing. But just look at the numbers. How do I combine a +2 and a -2 so they balance out? You're like, well, they already balance out. So when I combine this to make a molecule, I'm just going to take 1 calcium and 1 carbonate, and it's going to look just like that. And how do I name it? I name it with the name of the cation, which is calcium, and the name of the anion, in which case is carbonate here. And I call it calcium carbonate. The next example I have up here is sodium sulfate. Let's find sulfate on our table. SO4 2- is right here. That's sulfate. Now notice there's also something on the periodic table, or on the table here, called sulfite. What's the difference between sulfate and sulfite? Sulfate has 4 oxygens. Sulfite has 3 oxygens, but both of them have a -2 charge. So one letter makes a difference, and we have to pay attention to that as we go through. We'll see some examples. So sodium and sulfate. Sodium, we know, makes a +1. Sulfate, we look it up on our table until we can memorize it a little bit better. And it forms a -2 charge. How do I balance out a +1 and a -2? Regardless of what letters I put with them, I need 2 +1s to balance it out. And that's why I get Na2SO4. And I name that sodium sulfate. All right. Let's do another simple example before I go on to the next one. Let's pick chlorate here. Chlorate here is an ClO3 with a single minus charge. And so I'm going to write that down here. Scroll back down. I've got chlorate, ClO3 minus. Okay. Let's go ahead and pair that with magnesium. Now magnesium, what kind of charge does it have? It's an alkaline earth metal, so it's got a +2 charge. Mg2 plus and ClO3 minus. Now, how do I balance a +2 and a -1? I need 2 of the -1s. So I need a second ClO3 minus here in order to make this work. And I get Mg. Now, how do I put my 2 ClO3s there? Some people I see do this. They say Cl2O6, and technically it's not wrong because you've got 2 chlorines and you've got 6 oxygens, but we don't do that because it turns out when you write it that way, someone looking at it won't know that you had chlorate to begin with. And what we want to tell them is, hey, we've got 2 chlorates. And so what we do is we actually just put it in parentheses. And we say we've got chlorate, and we've got 2 of them. Mg, parentheses, ClO3, parentheses, 2. Magnesium chlorate. Now, our last example up here that we had was iron and phosphate, FePO4, iron 3 phosphate. Okay. Let's go ahead and work that out down here. FePO4, iron 3 phosphate. Well, if you look back up at that table, you're going to find that phosphate has a -3 charge. Now, if for phosphate to have a -3 charge, and if I tell you the formula is FePO4, what does that tell you about that iron? Well, if this guy's -3 and they balance out, this guy must be +3. And so you get Fe 3+ combined with PO4 3-. And that's how we knew there was a 3+ on that iron there, is by balancing that out. And we get iron 3 phosphate. All right, let's do another example where let's go from a formula to a name for something in the transition metals. And so next we'll take copper, and we're going to go ahead and take my copper, and we're going to combine it perhaps with NO3. What does that tell me? So I'm going to do this formula, and what I want to find is my name. How am I going to do that? Well, I know that Cu is copper. After a while, I learned that NO3, if I look up on the table, is an NO3-, and it's called nitrate. Right? And it's got a -1 charge. But I've got 2 of them. Right? That's what that 2 tells me. I've got 2 -1 charges. And so I've got -. In order for that to balance out, what does copper have to be? Well, if I've got a -2, copper needs to be a +2. It's the only way it's going to work out. And so we name this copper 2 nitrate. All right. Copper 2 nitrate. So going from a formula to a name, you've got to figure out your charges so that everything can balance out. Let me do one more example that's not always as easy for some people. Let's take something like manganese, and we're going to combine it with PO3 3-. If you look at PO3 3- on that table, it's called phosphite. Now manganese, what I'm going to do is I'm going to tell you that my formula is Mn3PO4 2. That's a much more complicated formula. And what I want to figure out is, what am I going to name Mn3PO4 2? Well, like I said, we now know phosphite is a -3. We've got 2 of them for a total of -6, which means that in order for everything to balance out, whatever we have for our manganese better darn well add up to +6 for everything to balance out. Well, I've got 3 manganese here, right? Mn, Mn, Mn. How am I going to get 3 things to add up to +6? Well, I just take 6 divided by 3, and I get that each one of those is 2+. It's a little bit of extra work to balance all those out, but you'll figure it out. And what do I end up with? I have Mn3PO4 2. I'm sorry, PO3. I have to correct myself up here. I'm correcting myself on the top there. PO3, because I have my phosphite, which is PO3, is called manganese. And I have 3 manganese, but remember what goes in the parentheses is the charge. Manganese 2 phosphite. All right. Somebody asked me once, why are we doing this? Why are we looking at all these common ions? Do we really use them? And the answer is yes. So one of the things I looked up just randomly was, what is in some common IV fluids? And if you look at this table here, you've got phosphates there, you've got hydrogen carbonates there, you've got our chlorides there, hydrogen carbonates, sulfates. So these are things that appear in the health field. They appear in all sorts of other chemical fields. They're good things to know. So here's a couple sheets where you get to do some naming practice. So I want you to start on this one, pause the video, and take some time to try to come up with names for that first column and formulas for that second column. Alrighty, here are some answers. MgF2, we know that magnesium is one of our alkaline earth metals. We don't need to put parentheses for the alkaline earth metals because we already know what it's called. So we call this magnesium fluoride. We don't have to say that there's two fluorines because there's only one way to do that. The next one, K, is potassium. And we call it oxide because oxygen is there. And we put the IDE to let us know we have an anion. Okay. The next one, beryllium chloride. And again, we don't need the parentheses there because we have something that's in the alkaline earth metals. The next one, though, nickel, we look and we see that it's a transition metal. As soon as we see it's a transition metal, we know we need the parentheses. And so when I write this, I'm just going to write nickel. I'm going to write some parentheses, and then I write the name of the O, which was oxide. And then what do I put in parentheses? Well, remember, it's got to balance out. Oxygen is -2, but there's two of them for a total of -4, which means that nickel better darn well be +4 to balance it out. And I get nickel 4 oxide. The next one, molybdenum and nitrogen. Molybdenum. And nitrogen is going to be called nitride, right? Because it's an ionic compound, a metal and a non-metal. But what charge do I put in there? We can figure this out the long way, right? Nitride we know is -3, which means there's a -6. Which means we've got a +6 total for our molybdenum. We have 3 of them, and so each of them is going to be +2. And so we put a 2 there, and we say that's molybdenum 2 nitride. Or we can do the switch rule here. Remember, 2s and 3s, the switch rule works really well, and we know that that 2 becomes the charge on the molybdenum. All right, here we've got some names. We're looking for the formulas. We've got strontium iodide. Strontium is Sr. And we look it up on the periodic table, it's 2+, iodine is -. How do we balance +2 and -1? Sri2. We need 2 iodines to balance that out. Lithium and sulfide, we start off by writing our charges. Li+, S2-. How do we balance that out? We need 2 lithiums to balance out my sulfur. Barium, Ba2+, nitride, N3-. Now, here's a hint. When you see that IDE, right, we have nitride. If you look at our table, we also have nitrate and nitrite. It's very easy to get those confused. When you see IDE as the ending, it almost always tells you that you have a single atom. Phosphide means you have phosphorus. Nitride means you have nitrogen. Oxide means you have oxygen. But if you have ate or ite, it means you have one of those polyatomic, one of those common ions. You've got nitrate, you've got NO3-. You've got nitrite, you've got NO2-. So look for those endings. Unfortunately, there's 2 exceptions to the IDE rule. IDE is almost always a single atom, except hydroxide, which is OH-, and cyanide, which is CN-. Other than those 2 exceptions, if you see the IDE, you know you have a single atom. If you see ate or ite, you know you have several atoms. All right, so here we're going to go down to titanium 4 bromide. That 4 tells me my charge is 4+. I've got a Br- here. How am I going to balance a +4 and a -1? I need 4 -1s, and I get TiBr4. The last one is palladium 2 sulfide. Palladium, if you look it up on the periodic table, is Pd. It's got a 2 plus. Sulfide has a 2 minus. When I combine those, I just get PdS. All right, so next we have more practice, because practice never hurts. Here we're using the common ions, and I've got part of the table printed there, so I want you to pause the video again and try to come up with names and formulas for these ones. All right, sodium, Na+, alkali metal. Nitrate, we look it up on the table, is NO3 with a minus charge. How do I combine a +1 and a -1? Just one of each of them, and I get NaNO3. Cesium sulfate, cesium, Cs, I find that on the periodic table. It's a +1. Sulfate, that ATE tells me I've got a common ion. It is SO4 2-. How do I combine a +1 and a -2? I need 2 +1s. Now you'll notice I didn't put a parentheses around the sulfate this time. When you only have one of them, you don't need the parentheses. It's just if you have more than one of your common ion, you need the parentheses. Iron 2 chlorate is Fe2+. That's what that 2 means. Chlorate, if you look over at the table, is ClO3-. I've got a +2 and a -1. I need 2 of the -1s, and so I get FeClO3 2, with that 2 on the outside of the parentheses. Magnesium. Here I want a name. So I start with magnesium, the name of my cation. And the nice thing is about these guys, I just need to give you the name of the anion here, which is cyanide. One of those exceptions to the IDE rule. And at last, I've got copper and phosphate. And so I write copper here. And I look, where's copper on the periodic table? It's a transition metal. If it's a transition metal, you're going to put those parentheses there. Okay. So copper, parentheses, I know it's going to be phosphate, because that's what PO4 is when I look at the table. But I just need to figure out the charge. Easiest way is the switch rule. Right, that 2 on the phosphate becomes the 2 on the copper charge. You can also do it by balancing out the charges, as we've been showing you before. So this was a long one. Sorry about the length. But we've now figured out how to take atoms, put them together, make these compounds, and then name them. And there's different ways of naming it. If we have an alkali metal, alkaline earth metal, we don't need to tell you about charges or anything like that, because alkali metals are always +1, alkaline earth metals always +2. If we've got a transition metal, somebody needs to tell you that charge. They're either going to tell it to you directly, they're going to tell it to you as part of the chemical name, like iron 3 something, or they're going to tell it to you as part of the formula. When we said, oh, if we've got FeBr2, we can use what we know about bromide to find that the charge of Fe is +2. And then we also talked about how to name with common ions. Same way of naming things as we did before, except we use the common ion name instead of the IDE name, nitride, oxide, and things like that. And it sounds very complicated. It is very complicated. The only way to learn this is practice, 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 practice. Find yourself worksheets on the web, do homework problems that I have, and practice this over and over again, because that's the only way you're going to learn it. All right, talk to you later.